Higher education is undergoing a structural transition. The historical model relies on broadcasting information to a passive audience from a single source. For decades, the professor operated as the sage on the stage, the primary, authoritative transmitter of facts. That framework is giving way to models where the instructor acts as a guide on the side, and students actively construct their own understanding through interaction and inquiry. Because of this shift, subject matter expertise is no longer the only requirement. To teach effectively, university faculty must now utilize formal tools grounded in cognitive science and educational psychology. The modern professor must operate as an architect, engineering an environment where learning is the unavoidable result of the student's experience. A common failure in university course design is confusing long-term strategy with short-term tactics, which leads to fragmented learning. Strategy is non-local. It defines what specific competencies the student must possess by the end of the degree program. Introducing a concept like the natural logarithm in week 1 is a strategic choice, acting as a load-bearing pillar for advanced modules later. Tactics, by contrast, are local. They govern the immediate execution of a specific lecture to keep students engaged. To build an evidence-based instructional design system, we must map the structural links from strategic goals, through biological constraints, down to specific classroom tactics. Tactical execution is only useful if it is subordinated to a cohesive, long-term strategic architecture. To define this strategic architecture, instructional designers use learning taxonomies to map cognitive growth. This illustrates the 2001 revision of Bloom's taxonomy. Notice the horizontal axis. Categories are active verbs, emphasizing learning as an active process. In this model, the apex of cognitive complexity is create. Generating a new intellectual product requires synthesizing all previous layers of knowledge. However, when assessing complex university assignments like essays or clinical evaluations, categorizing the task itself is less useful than measuring the structure of the student's actual response. The Solow taxonomy evaluates how an answer grows in quality. A novice provides a multistructural response, isolated facts. As understanding deepens, facts connect into a relational web. At the highest level, the extended abstract, students project that web outward, applying it to new contexts. Defining goals through active cognitive verbs removes subjectivity from academic grading and clarifies the target behavior. Before these strategic goals can be executed tactically, they must pass through the biological reality of the human brain. John Sweller's cognitive load theory maps this constraint. While long-term memory is vast, working memory acts as an extremely narrow, fragile pipe. Neurologically, human working memory can hold and process only 4 to 7 discrete units of information at once. Every lesson carries intrinsic load, the unavoidable complexity of the subject. Poor design creates extraneous load, friction from confusing formatting that chokes the brain's remaining capacity. Minimizing extraneous load leaves space for germane load, the productive effort required to build new neural schemas. If a professor fails to eliminate extraneous load, the bottleneck fills entirely, and schema construction becomes biologically impossible. Consider Mayer's redundancy principle. A common source of extraneous load is a presentation slide packed with dense text and charts, which the instructor reads aloud. Forcing the brain to simultaneously process conflicting visual text and auditory streams overwhelms limited working memory, which degrades comprehension. Managing this complexity budget introduces the expertise reversal effect. Highly structured, step-by-step tactics are essential for novices, but forcing an advanced student through that same rigid structure turns redundant information into harmful extraneous load. As a student's expertise grows, instructional support must dynamically decrease to allow space for independent problem-solving. Pedagogical tactics are not universally effective. Their value is relative to the student's current cognitive baseline. To map the biology of memory to specific lesson structures, instructional designers use Robert Gagne's 9 events of instruction as a tactical algorithm. Retrieving last week's material fulfills a strict neurobiological requirement. It activates the dormant networks needed to anchor new information. Adult learning relies on attaching new data to pre-existing neural networks. You must activate those networks before new connections form. In Event 6, Eliciting Performance, students generate responses. Simply listening to a lecturer is insufficient for encoding information into memory. Students must actively practice the target cognitive verb during the session to solidify the neural schema. Effective classroom tactics act as biological levers designed to force memory retrieval and permanent encoding. For designing short, targeted microlessons, the BOPPS model organizes the session into a 6-part cycle. The pre-assessment phase is critical. Measuring the baseline knowledge of the room before teaching prevents the extraneous load of redundant instruction. However, teaching complex professional skills requires a different approach. Breaking medical diagnostics or engineering down into isolated, atomized lessons strips away the necessary context. By contrast, the 4CID instructional model anchors learning entirely around authentic, real-world whole tasks. In these disciplines, procedural information, the specific steps of a task, is provided just in time while the student solves the larger, authentic problem. The scale and complexity of the discipline dictate the execution. Foundational concepts fit atomistic tactical models, while advanced professional skills require whole-task environments. John Biggs' concept of constructive alignment serves as the final synthesis of strategy, psychology, and tactics. It links intended learning outcomes directly to tactical activities and assessment tasks. In an aligned environment, a student cannot succeed on the assessment without executing the exact cognitive verbs defined in the initial strategy. When this alignment fails, it triggers the backwash effect. If a professor's strategy demands critical analysis, but the final assessment is a multiple-choice test on facts, the student bypasses the deep learning and shortcuts directly to surface memorization. Students are rational actors. They will always develop tactical learning strategies optimized solely for the metric used to grade them. If your assessment tests superficial knowledge is exactly and only what your course will produce. The debate between direct instruction and pure discovery learning is resolved by cognitive load theory. Throwing novices into discovery overloads their working memory and halts learning. The evidence points to guided inquiry as the optimal synthesis. Instructors provide scaffolding initially and systematically fade-vet support as the student builds internal cognitive schemas to handle the complexity. This defines the role of the modern university faculty member, an architect of cognitive environments who applies subject matter expertise to engineer the student's journey. By respecting biological constraints and aligning strategic vision with tactical execution, educators move from intuitive teaching toward a rigorous science of learning.